Hello, and a very good day for all our beloved lecturer. We are from Group 1. We are like to present about static and mechanic for our group assignment of real life example. So, our group consists of 5 members. Muhammad Aisar IQBAL bin RUZAINI, Muhammad AIDID SYAHMIM bin NORZAIDI, KATHIREVAN anak lelaki THAMIL CHELEVAN, ALEYA NAJWA binti SABRI, and NURUL ILYANI binti ISHAK. Welcome to the world of innovation in healthcare. Today, we delve into the realm of hospital equipment, specifically the examination bed. Beyond its apparent simplicity, the design and functionality of an examination bed intricately intertwined with principle of static and mechanic of material, showcasing a fascinating blend of engineering and medical care. In this presentation, we will explore how the examination bed, a seemingly mundane fixture in hospital, operates on the principle of static equilibrium and material science. By understanding the mechanic behind its design, we gain insight into how this bed provides both comfort and stability, ensuring the safety and well-being of patients during medical examination. The humble examination bed, a staple in medical facilities, stands as a silent testament to the intricate dance between static and mechanic of material within the realm of healthcare. Beyond its apparent simplicity lies a marvel of engineering designed to seamlessly balance force and ensure patient comfort during medical examination. In the world of static, the bed exemplifies equilibrium, strategically distributing loads to maintain stability. The mechanic of material comes into play as the bed, crafted from a fusion of robust material, withstand varying force and pressure. The meticulous design of the examination bed reflects a marriage between biomechanics and engineering precision, creating a platform where the principle of static equilibrium and material mechanics converge. As we explore the mechanic embedded in the structure, we unravel the symbiotic relationship between medical functionality and engineering ingenuity, showcasing how a seemingly mundane piece of furniture becomes a vital link in providing a secure, supportive environment for patients and a testament to the interdisciplinary nature of modern healthcare. In this video assignment, our primary objective is to showcase the mastery of static learning outcome through the lens of real-life example. We will delve into the fundamental of learning outcome number 1, where we utilize free body diagram to conduct equilibrium, best analyzed for a range of structure. Moving on to learning outcome number 2, we will tackle problem involving body subjected to axial, bending, and torsional load, unraveling the complexity of each scenario. Transitioning to learning outcome number 3, our focus will shift toward moment and inertia-based analysis, demonstrating their indispensable role in problem solving when faced with compound load. Additionally, we will explore learning outcome number 4, delving into the evaluation of stress and deformation within the realm of biomedical device, providing practical insight into their structural integrity. Finally, we will exemplify the importance of teamwork in learning outcome number 5, showcasing our collective effectiveness in analyzing real-life cases involving static objects under varying load. Through this real-world application, we aim to not only meet but surpass the learning outcome, bringing static to life in a tangible and meaningful manner.
So this is our problem statements of our assignment. The current examination bed that we can find in the market of most hospitals has its limitations, and problems can be identified by analyzing the stability and structural integrity. And this involves a series of physics formulas. For instance, many examination beds that we can find in hospitals have problems, especially if we want to adjust the height. And there is also problems associated with the backrest inclination and also leg support. So problems associated with the adjustability of examination bed often arise because the users are of a wide range of sizes. Therefore, we want to make improvements so that the examination beds can cater to a wide range of physical characteristics among users. Some of the parts of the examination beds that often experience impairments or problems are the hydraulic system, frame, welds, cushions, and others. This examination bed may suffer from uneven load distribution, affecting the comfort and safety of patients during medical examination. So the patients may experience localized pressure points, discomfort, or even potential injuries, especially when they are being used for an extended period of time. So the best examination bed design should be flexible and adaptable to accommodate different body types, sizes, and medical conditions, ensuring inclusivity in healthcare services. That being so, what are the physical conditions needed to be considered in order to design a flexible and robust examination bed? So these are the problem statements proposed by our group in order to design a flexible and robust examination bed. First, what are the forces exerted on the examination bed when a person lies on it in equilibrium condition? Second, what is the magnitude of normal stress when a load is applied on the examination bed? And the third is what is the maximum torque that can be exerted to the ratchet when adjusting the backrest. Ratchet is the bar connecting the backrest that allows motion in one direction of the backrest. So the fourth one is what is the required diameter of fastener of the hinge supporting the backrest when the allowable shearing stress in the shaft is 30 megapascal. And the last one is what is the maximum moment that a frame of the examination bed can withstand. So these are the procedures and methods taken by our group members for our assignment. First, we choose an examination bed from Karina Medical website. The second one, the problems associated with the structure and movement components of examination beds are identified, and the solutions for its improvements are proposed to improve the overall user experience for both healthcare professionals and patients. And the third one, before we conduct the structural analysis, the measurements of the components of examination bed, such as the dimensions of the table and back section and length of the frames, are noted, and photos of the examination bed are taken. These are done by assessing Karina Medical website. The fourth one, we make assumptions for the analysis, and factors like load, stress, and forces are drawn to be exerted on the structure for structural analysis. And we also use the help of free body diagrams. Calculations are made using a series of formulas. Next, distribution of forces on the members of the structure is analysed to identify the likelihood of malfunctions and breakdowns due to compounding loadings. And the last one, a written report is prepared showing the findings and the results of the assignment.
So now let's move on to results and calculations. So first thing we're going to calculate is the equilibrium. So our question here is create a free body diagram of the examination bed, determine the magnitude and direction of external forces and the body weight acting on the examination bed. So this is a picture of our examination bed. Here we have our measurements for the examination bed, and here we will assume a couple things. One, the examination bed is an inclined plane at 60 degrees, and the force acting on the examination bed is the weight of the human upper body. So here it's 1005.48 newtons. So another assumption made is that the support bar is at a ratio of 2 to 3 of the backrest. So the first portion is 0.24 and the second portion is 0.36 meters. The support bar exerts a force of Fc against the backrest, and there's a hinge at point A. So now let's calculate the sum of Fx equals to 0 and the sum of Fy equals to 0. We write down the equation as shown here, and then the sum of moment at point A equals to 0. Here we get our Fc value, which is 1256.85 newtons. After getting our Fc value, we plug that back into our Fx and Fy equation. So we get our answers here. Fx equals to 217.7 newton at anti-clockwise, and Fy gets 125.7 newton clockwise. So now let's talk about the stress axial loading. So our question here is to determine the stress distribution of one of the legs of the examination bed. By definition of stress is pressure per unit area. So here we have our man sitting at the end of the bed here. So we're going to calculate the stress distribution at one of the legs. So here we have a diagram of our bed, and the highlighted blue region is the leg that we want to calculate. So the assumptions made in this calculation is that the maximum human weight for the patient will be 150 kilograms. So we convert that into weight and we divide that by 2, as we assume that the weight of the human body is spread evenly between both the legs at the edge of the bed. And since we only want to calculate one, so we divide that value by 2, so we get 735.75 newtons. Another assumption that was made is that the region of cross-section taken is perpendicular to the longitudinal axis of the leg of the examination table, and the region of cross-section taken is assumed to be the same as the cross-section of the rest of the leg. So now let's continue to the calculation. So pressure per area, let's find the area first. We assume that the width is 25 millimeters, and we multiply that by the length, which is 5 millimeters, and we get a value of 1.25 times 10 to the power of negative 3 meters square after conversion. So we plug those two values into the formula pressure over area, and we get an answer of 58.9 times 10 to the power of 5 newton per meter square. Moving on to torsion. So now let's look at our question here. In between the backrest and the bed, there is a hinge. Given an allowable shearing stress of 30 megapascals and applied torque is 100 newton meters, use the elastic torsion formula to find the required diameter of the hinge. So on the left, you will see a drawing of the hinge underneath the backrest and the main body of the bed. And below that, you will see the drawing of the hinge and the inner cylinder in green color and the outer cylinder in black, and the torque of 100 newton meters that was assumed. So here we also assume that the inner cylinder is solid. So we can see the shaft drawing of the hinge here. And let's cut out the first part, so we will get only the A region. And here we can find our A region, and the moment around the A, which I denoted here as sum of mx equals to 0. So 100 minus the TAB, which is moving in the opposite direction. So we will get TAB equals to 100 nanometers. So we will use the formula of maximum allowable shearing stress equals to TC over J, where Yj equals to pi over 2 times by C power 4. So now we will use the formula of allowable shearing stress equals to TC over J, where J equals to pi over 2 times by C to the power of 4. We'll plug that into the equation and we'll rearrange it, so it becomes allowable shearing stress equals to TAB divided by pi over 2 times by C to the power of 3. And we will get our answer, which is C equals to 0.01285, and C is the radius, so we have to multiply that by 2 to get the diameter. So our diameter here is 0.026 meters.
Now we're coming to shear stress. So we have 3 things to calculate, which is the first one is to find the shear stress on the bow if 200 Newton vertical force is applied on it, and then we have to determine whether the bow is strong enough to withstand the shear force, and we have to determine the force at which the bow will break. By assuming that the diameter of the bow is 1.3 centimeter, the cross-sectional area of the metal bow can be calculated as 1.327 times 10 to the power of negative 4 meters squared. And to find the shear stress when the vertical force at 200 Newton meter is applied on it, we will be using the formula tau as in shear stress equal to F over A, and we'll get the shear stress as 1507159.005 Pascal as the shear stress. And then to determine whether the bowl is strong enough to withstand the vertical force at 200 Newton, we will be assuming that the bowl class is grade 8 and is made of stainless steel. So the shear strength will be considered as 640 megapascal for the bowl. And so we can conclude that the bowl is strong enough to withstand the shear force. And the last thing that we have to calculate, which is the maximum force before the bowl break, we'll be using the same formula, and we'll be using the 640 megapascal as the tau max, and we'll get 84.93 kilonewton as the maximum shear force that it can withstand before it break or experience failure.
Okay, so we move to the bending part, which is the question asks for using the allowable stress of 358 megapascal, determine the bending moment mx and my that can be applied to the Y-flage beam of the examination bed, and determine the largest moment m that can be applied. So we move to the calculation part. First of all, the diagram shows about the cross-sectional area of the beam. So we need to, first of all, we need to search for the moment of inertia. So we need to find for the I at C, which is 1 over 12 BHQ. So for the moment, we had to use for our formula I prime at C equal to 1 over 12 BHQ plus AD squared. So we are assuming maximum allowable shear stress is 358 megapascal. So we substitute the value into the formula. So the I1 is equal to 0.0I7 017228009 M4. So for the shape tree, since it has the same dimensions and same distance to neutral axis, so the shape tree will have the same value for moment of inertia. Then we move to shape 2, we use the same formula, which is I at C equal to 1 over 12 BH cubed. So we substitute the value and we got 0.016125 MO. M power 4. And then we need to calculate the sum up of the moment of the cross section word flinch. So the I total is equal to I1 plus I2 plus I3. So we need to sum up, and then it's equal to 0.05058 M4. So and then we got to find out the shear stress, which is the formula is shear stress equal to moment times with the distance to the centroid and over to I total. And then we need to do some algebraic equation, which is we have to find the Ms. So Ms equal to shear stress times to I total over the distance to the centroid. So Ms we substitute the value, and then finally we got 21.7 times megapascal meter. And then this question also asks about a moment for my. So we had to do the same as we used to find the mx. So first of all, we need to find the moment of inertia for y-axis, and then so I1 equal to b cubed h over 12. So we substitute the value. Then the I1 is equal to 6.029 times to 10 power of negative 4 m4. So it is same as calculation before, which is the I1 is equal to I3, and then the value is still the same. And then we move to the shape 2, which is we substitute also the value, which is 1 over 12, 0.05 cube times to 1.57, and then the I2 we got 1.635 times to 10 power of negative 5 m4. So we need to also to sum up the I total, which is I1 plus I2 plus I3, and then the total we got 1.222 times to 10 power of negative 3. And then we also need to do as the same as the to find the mx. We need to find for the my, and then we still have to do the algebraic equation, and then we got the my is equal to shear stress times to I total over the distance to the centroid, and then we substitute the value, and then finally we got 1.67 times 10 power of 3 nm. So when we compare the value with mx to the with my, we got the largest moment m that can be applied, which is 21.7 times to 10 power of 6 nm, which is a mega newton meter.
Discussions part of the video where we will be discussing ways to reduce risk of failures and deformation and suggestions for improvement of the examination bed. Reduce the risk of failures and deformation, we will be looking at the formula and the calculation that has been done. So for torsion, we can see that by increasing the diameter of the hinge fastener, it can withstand a greater shearing stress from patients with greater body mass. For shear stress that is experienced by the bow, we can see that using bow with greater surface area can increase the maximum shear stress that could be exerted on the bow before it breaks. And last but not least, for pure bending acting on the beam supporting the bed frame, we can see that by increasing the axis radius can lead to smaller moment of inertia and reduce the compressive or tensile stress experienced by the beam. On to the suggestion for improvement, we will be talking from a few aspects, such as the bed frame, the bed rest, the mattress, and the hand level. So for the bed frame, the beam underneath the bed has a tendency to bend over time with varieties of weight range of patients using it. So we are suggesting that putting trusses under the bed can give extra support as shown in the figure. And then the bowl for the frame might become loose after a long usage and cause instability to the bed frame. Therefore, frequent check and maintenance for the bowl is highly suggested. Rest, the support behind the backrest bends after a long usage and is not steady enough. Therefore, replacing the support with a thicker support can increase its strength. Also, the hinge connecting the backrest and the bed frame becomes rusty and hard to adjust. So, applying a rust-inhibiting coatings or lubricants to prevent the rust formation is also highly recommended. The cushion cover is torn and worn after a long period of usage. So, substituting the leather cover with a higher quality leather with higher durability to shear stress and abrasion is much suitable for an improvement. Then, the cushion becomes thinner due to uneven load distributions. So, by replacing the cushion with a new cushion after a predetermined period of time can solve that problem. Then we have the hand level and the backrest adjuster. It becomes rusty and hard to turn, so we will use a lever made from stainless steel, which is rust resistant, or apply rust inhibiting coatings or lubricants to prevent rust formation as an improvement to the bed.
So in summary, we discussed how the examination bed works using basic engineering ideas to check how its structures perform. We use diagrams to understand balance and solve problems related to different kinds of flows. We also look at how forces and bendings affect biomedical devices such as examination bed using techniques that focus on moments and inertia. The analysis of forces acting upon the examination bed provided key information about the distribution of loads and the impact on the components of the examination bed such as headrest, leg of the bed, hinge, and the frame of the examination bed. So the internal moments and forces of the components of the examination bed shedding light to the complexities of the structures. We have to take in order to reduce the stress, we have to increase the cross-sectional area, which is A of the bar. In order to reduce stress, we have to increase the cross-sectional area of the bar. To obtain the maximum torque T that can withstand the hinge, we need to increase the value of polar moment of inertia J, since the torque is increasing proportionally with J, which also increase the cross-sectional area of the bolt. In order to obtain maximum shear force that can be applied to the bolt. Last but not least, to decrease the compressive or tensile stress sigma withstand by the material of the beam of the frame or base, which is stainless steel, we can increase the moment of inertia I of the beam by increasing the radius of the beam. In essence, this report has not only fulfilled the objective on demonstrating the statics and mechanics, but has also provided a foundation for understanding and improving the biomedical aspects of examination bed. By connecting theoretical ideas with the real world use, this study helps advance biomedical engineering. It highlights the importance of accuracy, safety, user comfort in designing and using this device. So it is a promise. Thank you.